This is the first video in a chapter on advanced theories of bonding. We are going to start out by talking about valence bond theory, one of two theories used to help explain the gaps left by Vesper theory and Lewis theory. So far, we have discussed atomic orbitals where electrons live. S orbitals, p orbitals, d orbitals, and f orbitals, and the quantum numbers that describe them. We talked about orbitals. Oops, and we talked about the bonds that electrons form between atoms. It has been really electron-centric for a while. So we had the sort of theory that said there are atomic orbitals. So there's an s orbital and 3 different p orbitals around a particular atomic center. You can make anything out of that absolutely insane shape that I have just drawn. So we talked about atomic orbitals, and we talked about the bonding and the geometry of molecules, what shape they are in space, how the electrons are shared in a bond. But how do those two ideas fit together? You'll notice we didn't actually mention which orbitals each of these bonding and lone pairs lived in. So the question for today is, how do these two ideas fit together? Which orbitals are used for this bonding process? So we're going to fill in the gaps using two bonding theories that are widely accepted in the scientific communities, each of them having their own benefits and setbacks. The first of those is called valence bond theory. And the second will be called molecular orbital theory. So we'll talk about valence bond theory today, and we'll talk about molecular orbital theory next. So, valence bond theory. What is it? Why is it important? Why are we even talking about it? So the main facet of valence bond theory says covalent bonds form when half-filled atomic orbitals overlap. And this is a concept we briefly touched on before, but now it is going to be your new favorite word, orbital overlap. The orbital overlap is about the orbitals physically overlapping in space so that the electrons can exist in both of the orbitals at the same time. And we need several things to be true in order to achieve good, high quality, strong orbital overlap to make a strong bond. So it depends on 3 things. To get good overlap, we need the appropriate distance between the orbitals, the appropriate orientation of each orbital, and a good energy match. We're going to look at each of those 3 things in valence bond theory. So let's start with the first one, orbital distance. So we have already talked about this, but we'll bring it back just so that the story is complete at this point. Remember a few videos ago, when we first learned about covalent bonding, when we drew a plot that looks like this, with potential energy on the y-axis and the internuclear distance on the x-axis. Remember, the internuclear distance is the distance between two nuclei. And so we said that this plot looks roughly like this. And we separated it into three regions based on how far or near the distance between the two nuclei or the two orbitals might be. So over here on the right side, we said the internuclear distance was large. There's essentially no orbital overlap and no interaction between atoms when they're very far apart. So we've set the energy to be at 0. As the nuclei and the orbitals move closer and closer together, as we move to the left in the graph, we eventually reach an energy minimum at the lowest point of the graph. And we know that low energy is stable. So this is the ideal internuclear distance, also known as the bond length. So this is where the atoms are appropriately distanced so that there is a small amount of overlap indicated by this picture. So we have good overlap between the orbitals. That results in bonding. And we know that when we move from a state with higher energy to a state with lower energy, that energy has to go somewhere, so that energy is released when a bond is formed. Because a bond is so favorable, the atoms will literally give anything to be able to be in that bond. Energy is released when a bond is formed, because a bond is an energy minimum. So if the atoms are far apart, there is no orbital overlap. If they start to become closer together and they reach an ideal distance between them, there is good overlap and we get a bond. If we continue to move them closer to each other over in this left side of the plot, we reach a place where there is such a thing as too much of a good thing, and those orbitals are too close together. We have too much overlap because the positively charged nuclei start to repel each other, and it's just a bad time. So there is such a thing as too much or too little overlap. We are looking for the appropriate bond distance to have the best orbital overlap. In the next video, we will talk about the next feature of good orbital overlap, which is orbital orientation.